All right. Good afternoon, everyone. Um uh, Today's guest is Dr. Al-amin Bugaje. So Al-amin Bashir Bugaje has a PhD in electrical engineering from Imperial College London. His PhD research focused on machine learning-based dynamic security assessment and control of electrical grids. Al-amin is currently a research engineer at EDF R&D, where he works on unlocking residential flexibility for an agile electricity system. His talk today will cover his research and research journey, teasing out the power system of the future. Thank you very much, sir, for honoring our invitation. The floor is yours. Thank you.
Yeah. Hi, morning or afternoon, I guess, where you are right now.
Afternoon, 2 p.m.
Yeah, and thank you very much for the invitation to be with you. Sorry about that. For the invitation to be here with you. I'm really quite excited to talk to you on some of my journey and perspectives from power systems from a newbie researcher, and some learning points I think that I took along the way that it's worth perhaps emphasizing when you're going into research and framing your mind along those lines. To start with, I think it's always important to sketch out an outline of a talk just to prepare what is going to come. And in so doing, well, if halfway through you want to leave, you sort of know you're not missing too much, but really just for a mental map. And the first, I will start with a quick sketch out of my journey from a BIOS perspective, and subsequently try to answer, at least from my own perspective, why a PhD and how you need to think about it from a global perspective and try to connect some higher dots of motivation. And on a high level, as much as I can, just talk about what I've researched or tried to research in the last couple of years in terms of current work, which happy to go through a little bit of what the motivation is and why that sort of work was important in the first place, and then segue into this new line of thinking of machine learning-based dynamic security assessment, and sketch out what the problem of some of my thesis was trying to answer in trying to say, how can we improve this? How can we make it better? Or what sort of are the pending questions in there? I think subsequently, and more importantly, just tease out what is going to come subsequently. And this is the transition of power systems into low inertia when you incorporate a lot of renewable energy sources, and think about from a model perspective how you could think about combining physics with data-driven methods to solve some of the challenges of purely data-driven methods. And finally, talk about flexibility from a DER's perspective, which is, I think, gaining some traction right now. All right. I think from the bio, it's worth maybe spending a little bit of time where I think started this journey from Ahmadu Bello University, which perhaps some of you may be aware of. That's where I met where I met Ali, and who was kind enough to extend this gracious invitation. But at Ahmadu Bello University, my bachelor was in electrical engineering. Spent 5 years in there, but most notably was my final year project where I started thinking about real-time energy monitoring systems as a way to, very similar to what was happening in Europe, although at a much micro scale, thinking about how you can monitor your energy consumption such that when there was like a crazy tariff hike bill, thinking about how can you put in local energy monitoring places to sort of be able to help with that in a way through some form of providence luck. I graduated and got a full ride scholarship and went to Imperial College London at 2018, where I then started my master's in future power networks. Spent a year, did my final year thesis with Dr. Kremer, working on machine learning based dynamic security assessment. And, you know, we really clicked with the group. I had the option of going elsewhere for my PhD, but which I'll come back to it. There was a lot of, the dynamics were good. We sort of understood each other. We were operating on very similar wavelengths. So I decided to sort of stay within that group, which was quite fortuitous, where I did the PhD in the control and power group, working on very similar topics. And I had the opportunity somewhere in there to go to the Delft AI lab at TU Delft in the Netherlands, as a visiting researcher. And through my PhD have been part of the IEEE working group on the big data analytics on transmission system dynamic security assessment. And really, I think just high level, other type of activities beyond the academia is the emphasis of community and outreach programs, which I think this part of programs sort of qualify in that, and it's sort of very much shaped my journey. For example, at ABU was doing Tide, was doing other sort of community programs and teaching. At Imperial was part of the Athenes One committee, was doing a lot of teaching, was doing a lot of outreach, was working with the graduate school, doing the departmental representative as a volunteer, and as well in Delft, sort of organizing seminars and the Delft AI product launch. And what that helps you with is giving you a network of potential collaborators, but also friends that you could sort of count on. Now, in here, the next part of this talk is then talking about why a PhD, at least from my perspective. And I think it's very important to sort of center this into something beyond yourself. And for me, it was trying to then think about what were those questions that I was really passionate about. And is there any way that you can find a way to connect those dots? Sometimes you're quite lucky enough that you can tease out and go very deeply into a topic that you're very passionate about until you tease out all the salient points. Other times you find a way to either by the side within that field, make them connect. And the two motivating questions have always been the issue of energy poverty, which if you could potentially zoom in here, you would conspicuously see that the sub-Saharan region, but Nigeria here that we are, is really energy poor. And there's a very strong correlation between development and per capita energy consumption. And this, I mean, growing up in the society that I did was something that is glaringly obvious to you. It hits you in the face, and have always been sort of a key thing. Now, the second motivating question is a bit more existential, and it's the question that, well, it's warming, right? And the global temperatures are sort of rising. Climate change is real in however way you want to frame it. And the question then is, how then do you combine these into something? And in trying to, on some level, on the side notes, doing some work, teasing out what the future potentially for Africa, sub-Saharan Africa, Nigeria in particular, is going to look like. But also, if you are trying then to sort of burrow down from a power systems perspective, what is the implication of climate change? I think these were what we're driving. And it's very important as far as in my experience, because there are going to be times when it's not going to be all pretty. You're going to feel tired, demotivated. And somehow, if you're able to, there are a lot of other stuff that helps, but if you're able to connect it back to the bigger motivation, it's always very nice and easy. Quick highlights. I'm going to start rushing through it now. Just some stuff, but highlights of some of the PhD experience I've gotten was that you're quite blessed with new perspectives, in that academia is always sort of this fertile ground of rich minds that come together and can be really quite something stimulating, keeps you young. I can see sort of sometimes the old professors and the value they even get just interacting with sort of people from different perspectives, with different ways of thinking, which was really quite something. And if you're sort of quite particular about a vision, then it can help with actualization, where you're working on stuff that matters, and there are certain skill sets that you pick up in terms of troubleshooting, in terms of thinking about a problem, in terms of other soft skills, which I would talk about, that become invaluable in the future. However, there's still some considerations to think about, right? Because really, I don't want to glamorize sort of the PhD journey. And I think anyone who has gone through that, depending on where, would attest to some fact of it not being trivial. And the idea that, to make a contribution or a novel contribution, you really have to get to the edge and then push it a little further. And for the most part, I mean, you would get some support, and for the most part, it's all you're doing. And while it is possible, while it is easy in a way, it really isn't trivial. It's something that requires your whole being, and you have to get very comfortable with failure, basically. Something that also stood out very, very curiously was actually, even for something as technical as engineering and power systems and stuff, your soft skills are as important as the technical skills. And perhaps there is some semantics here as what you want to talk about as soft skills versus hard skills. But the skills of writing, of presentations, of critical thinking and reading are as important as all the code that you can think about, as all the software that you can program and stuff. If the results come out, you have to find a narrative to connect the dots. And really, it's sort of this mesh of skills coming together to somehow just make things into this flurry of quite an interesting bit. And then finally, something that I really want to emphasize, and it doesn't have to be for research or PhD or whatever, it's that if you want to improve on anything, feedback is your growth pattern. And you, from the PhD's perspective, always lean on to sort of your supervision team, or get a really good peer group that you can lean on. And the richness of this is I find, or I saw a lot of people coming in and basically I don't know, sometimes waiting for the supervisor to get them to write a draft, or um, almost being quite passive with the whole process. But in fact, just assume that the first draft is always crap. Assume that sort of the ideas need fine tuning. Assume that because the whole process is it's this iterative process where ideas and knowledge, sort of mash into something quite beautiful at the end. So you want to get that fine tuned as much as possible. You want to get those ideas critiqued. You want to get those ideas polished, if you will, and you need feedback. So done talking about the high level stuff, I try to burrow perhaps very quickly in the next 10, 12 minutes. Um, yeah, what sort of my current work or what previous work was sort of focusing on. And I think to just tease it out, um, if if you are aware of how power comes into your house, then this part is not for you. If you're not on a high level, power system architectures were sort of designed in a centralized fashion where you get some generation probably from coal or something quite stable, gas or hydro. And then you send that power in through a network of lines and cables interconnected together, operating at very high voltages, step it down to distribution. And then that light comes to your home to power your homes, light bulbs, kettles, and everything. But the key part is that it's a centralized fashion. And then at the center of this architecture, the system operator sits, trying to make sure that everything is going steady. And by going steady, I mean in real time, demand must be matched with supply. And there are regulations around frequency for different countries, but it's quite a tricky system in that, the energy that you're going to use to boil your kettle does not actually get transmitted until you've pressed that kettle button, which makes it really tricky to handle with intermittency and variability, which then leads to the motivation of why do we care, or what's changing and what's quite interesting about it. And then when you zoom into that architecture, the changes that you're observing are that in the distribution, you're getting in some countries a lot of rooftop PV coming in, a lot of wind and solar coming at the high voltage level, some batteries and some stuff. But really what it all does is that it's taken in a lot of more uncertainty, both from flexible generation and flexible demand. And that uncertainty somehow complicates the level of power systems operations. And a quite interesting example in the UK in 2019, there was a time when two power stations went offline, and there were millions of customers that were affected, including disruptions of train services. And really what happens when there's a blackout anywhere in the world, in Nigeria as it were, um, when you lose generation, your frequency sort of, at this point, you lose your power and then it tries to slip off. And beyond a certain point, synchronism from your machine sort of get lost. And so, yeah, some parts of the network has to be disconnected. And then obviously some control measures were then taken to sort of bring the system back to stability. But the question is, could this have been anticipated? And was there a faster way to sort of do that? And in that that teased out sort of the motivation of my line of research, where, well, perhaps if we have a lot of data or we can use this AI thingy, then maybe we can very quickly assess the post-fault security of the system. And I just want to, I know there's a lot of fab. So in this particular context of research, really, you don't quite need data-driven methods. However, the advantage is as you're moving, to sort of time horizons that are much faster towards real-time control, there's a lot of complexity of power systems because the big power systems can contain thousands of buses, and then you have to analyze, hundreds of thousands of points, sometimes it could be a million, depending on how extensive you want to be. And you need to test faults, that if you use the conventional time domain simulations, they are ridiculously slow, that it becomes intractable to scale it up to big systems. And the question is, if we have a lot of data coming in as part of monitoring, or but as part of all the new techniques sort of being developed, then perhaps you could leverage that, into designing smarter systems. And then this sort of workflow was then developed in the 80s, where was trying to create this two-stage approaches where offline you get some data by some way. And by data, explain that very quickly. You'd get some data and then you train some model. And then with that model, you then assess very quickly and possibly take some control actions. Now, how do you get that data? So if it's not historical data, then what you do is for a particular operating condition. And so this is for example, the power levels that the generators are working on, the voltages in the system, the phase angles. You sort of get some form of system parameters, and then you do an analysis, a dynamic security analysis, where you figure out, if you simulate a fault, is the system able to recover as it did, for example, with the UK example, or if there's a fault, is the system cascading back into a blackout, a permanent blackout, where you sort of go days or weeks without lights. And then with this, you sort of then get your labels of whether the system is going to be safe, 0, or unsafe, 1. It's like a binary classification problem. And then you use this data to train your model, and then very close to real time, you can sort of use this for prediction of this, for example, hyperparameter boundary separating the insecure, unsecure conditions. And the key point is just the fastness. However, there are certain challenges that you need to address. I'm sorry, just 1 second. And the challenges are that if you look at it as a prediction problem, if you're at a particular time of your day, you don't actually know what the load is going to be, or the generator is going to be at a particular point. And if you remember the point about how load and generation must be matched in real time, then there's a need to know, firstly, what that particular condition is going to be X plus 10 into the future hours. But actually, there's a lot of uncertainty coming with that, your prediction or forecast, even though methods are getting better, but you're not quite sure which realization is going to be. It could be this, it could be that, it could be all of these other stuff. So there's uncertainty with the forecast of the predictions. The second part of it is that, well, if your model, your ML model sort of makes a prediction that the system is safe, it's not necessarily true that your system is going to be safe, that nothing is going to collapse, as it were. And this comes to the sort of cost imbalance, in that the predicted security and what the actual security are closer to real time may be very different. And really, there's a different cost attached to when you get a prediction wrong. And in sort of these type of problems, if you say the system is safe, but actually it's not safe, then it's almost like you're inviting a lot of trouble where your system can collapse. However, if you say the system is actually not safe, well, it is safe, then really the maximum you just sort of maybe is going to be a bit more expensive operation for you, where you do some redispatch and stuff. However, if you get it wrong and it's actually not secure, then that's sort of big trouble. So there's this disparity in the sensitivities of the cost. Now, thinking about this particular context and this particular transition and these particular problems, you can somehow formalize this into this sort of workflow, as I've tried to explain earlier, where there's an offline stage and then there's an online stage, and then you do some sort of control. And this pipeline of work has been worked on for sort of the last decades and so. But, quite curiously, and, always if you want to start something, for me, sort of start from the beginning or the end, however you want to think about it. But curiously, if you look at this pipeline, there's a huge assumption being made here in that you're feeding this process good data, or you're generating good data. And it's this assumption that you have quality data. And this assumption is not trivial, because if you assume, or the assumption of quality data, it's very much saying that your classifier or your model is going to be really good. In fact, you could argue that all the predictive performance of any model is simply a reflection of the quality of its data. And by data in this context, quality, I mean, so it's the coverage, it's the variability, it's the balance of the different labels relative to some of the problems I tried to tease out. And why is this important? So in dynamic security assessment, unlike other ML applications where historical data is enough, so you can just observe what the system has done and try to get some model to be able to learn or predict based on historical patterns, it's not enough to just rely on historical data, because the times when the systems are going to be unsafe or going to insecure, most likely they've never occurred, but we need to sort of understand them or tease them out. So there's sort of this imperative need to sort of create synthetic data points. And my primary research on some level, one part of my thesis was then trying to answer this question: how do you generate quality data to train really good classifiers? And not going into any details, but there were 3 buckets of approaches trying to approach this problem, where each bucket of approach was trying to maximize a particular certain property. And what I was trying to do was, how can I get as close to the middle, where I try to balance all these contrasting properties? The first property, in a way, is the historical samples, where, for example, we've observed certain operating conditions happening. And this is just a hypothetical power injections A and B. And it has sort of following some distribution in a way. And the idea here is, can you generate data that tries to follow this distribution? But obviously, we've discussed the pitfalls that if you just focus on historical data and then sampling in here, then you're going to miss out on conditions that do not follow this distribution. The second part of approaches, we're then trying to say, look, well, it's a classification problem at the end of the day. So can we use that to our advantage? Can we try to focus into those quote unquote relevant areas that our classifier sort of needs data from? So hypothetically, the boundary. And the challenge with these approaches is that really it's not trivial to locate these boundaries, especially if it's not static, and if the feasible space is non-convex. And then the third approach was sort of then trying to tease out, can you actually ignore everything? Try to model somehow the physical feasible space and sample everything. Now, obviously, it's not possible to sample everything. And then what leads in there is then what is enough? And then trying to understand how much data or what kind of data are you trying to synthetically generate. And my research was then taken into this direction and trying to combine all the different properties in some interesting way. Sorry, just 1 second. I need water. Hmm. Yeah, thank you about that. We're almost nearing the end, hopefully. But yeah, with future work, I'm trying to then maybe pose some new questions where if someone wants to go into research in this direction, could be quite interesting perhaps to think about. But the first bit, I think, trying to highlight some of the work here where we did is, if you look at this pipeline that we've introduced earlier, where you have a workflow of ML-based dynamic security assessment. Most of the studies previously done in the past and the conception of the idea was based on power systems that were dominated by synchronous machines, and therefore you could say possessing very high inertia. And inertia is this ability of the power system to organically respond to load. So think about like a spinning wheel. If you change the load somehow, it's able to somehow just convert some of that kinetic energy to organically respond to load, which we need actually to um, balance demand and supply in real time. But then, what happens when the power systems are changing, and depends on what part of it. But from a centralized architecture, if you're taking in a lot of renewable energy sources on the transmission side, but also in the distribution side, those they are interfaced um, through a converter, which then introduce electronics, which then means they're operating with switches, which introduce very fast dynamics into the whole system, in addition to low inertia. But so the main change is that you have sort of, remember the changing landscape of architecture, you have these devices coming in, introducing a lot of faster dynamics. And there's firstly a big question of, is this workflow still working, or is it going to be working? Do we need to make new assumptions? Do we need to rethink how we approach this? And from a data generation perspective, which is part of what I sort of tried to investigate, we did some studies which was at least showing from a security perspective, actually the levels of your generations are a much stronger indicator relative to in previous systems when sort of the phase angles were enough. And in fact, it could be that, you don't need as much sophisticated models to train in low inertia systems when perhaps the boundary is very much separable. Like a linear classifier, a very straightforward classifier can tell you that this region is unsecure while this is secure. But from a high dimensional perspective with high inertia systems, you probably need some neural network to try to tease out sort of n-dimensional spaces where the hyperparameter boundaries are. But there's a lot of work going in this direction, and part of what we're doing with the working group is try to curate test systems with different data points and test systems to tease out, benchmark some of these methods and stuff. The next type of stuff is thinking about, from a high level, how can you make the data-driven methods better? From a power systems sort of operation. And part of the, I think, challenges were that because operating the power system is um, such a sensitive thing, that system operators sort of require trust before they take in any new models. And typically, what has resulted in that was, for example, the preference of very simple approaches like decision trees against sort of neural networks, because you can understand the decision-making process of a decision tree rather than the hulala boo that your neural network is going to be very accurate, but you don't quite know what's happening beneath the hood. And really, there are certain challenges happening with deep learning in terms of sort of the high requirements of training data, the inconsistencies of the solution or physical inconsistencies of the solution, and low generalizability and interpretability. And there's this new line of work thinking about how physics-informed neural networks can address some of these challenges, incorporating already known physics into the deep learning methodology, as it were. And there are like four streams of physics-informed neural network with the initialization, informing the loss function in the architectural design of sort of systems, but in hybrid physics deep learning models. One I'm particularly interested in is sort of from a power systems perspective is the graph neural networks, where you can then think about the power systems as sort of a connection of nodes as the buses, and then lines as the transmission lines, where that can somehow map into a neural network, for example, architecture. And all of a sudden, then the hidden and output layers of a neural network, can be attached to a physical meaning and can be constrained such that, they are aware of sort of how power is flowing and some of those fundamentals of Kirchhoff's law, as it were. And, it's quite promising in terms of being able to sort of aggregate, information from nearest neighbors to be able to do some stuff. And it's sort of aware of how, things are going to pan out. Finally, I think it's worth highlighting that another big change happening with even centralized systems, perhaps in sub-Saharan Africa and the rest, there's a lot of, I think, push in developing off-grid energy systems, mini grids, microgrids, as it were, independently and simultaneously developed, and at some point perhaps meshed together, connected all together. But for systems that have already matured power systems, there's a lot of push in trying to decentralize these systems. And this is coming from trying to get flexibility from the local sources, especially when you have sort of electrification of the heat and transport. So in places where it gets really cold, sort of use gas or hydrogen potentially, but also flexibility from buildings and flexibility from, EVs hypothetically. But the idea of flexibility is, can you adapt your energy consumption profile based on price signals in a way? So if there's not enough generation on the system, can we somehow coordinate demand, or residential demand or industrial demand or whatever demand, to be able to match more the generation profile? And then all of that then teases out from an architecture perspective, how do you do that coordination with the distribution and the transmission? Because if you remember, the normal architecture, you generate power, you send it out through the transmission and distribution, and it gets to the homes. If you're going to activate flexibility, and it's quite an exciting idea of perhaps how do you use that to effectively take in a lot of renewable and take out that uncertainty. But what you're effectively doing is you are then sending power back out. And when you're sending power back out the other way direction, the system or traditional systems were not designed for that. And then you get into, I don't know, voltage issues, you get into different, I guess, system needs where the transmission side is looking for something else, and then the distribution side may be, looking for something else, or it may be constrained that it cannot, send power back hypothetically. But really, what's quite interesting is potentially you could envision some flexibility operator, sort of, trying to manage these local resources of EVs and other stuff to support local networks in events or in the events of fault on the transmission side. Then there are questions about, how do you, for example, coordinated development of EV chargers. So is there a way that you can distribute it around such that it's still serving people's need, but you can use this infrastructure to coordinate sort of the response in terms of fault using these resources, and sort of somehow overlapping EV charging network infrastructure with the distribution electrical network using sort of geographical data and predicting EV demand for flexibility services. And sort of that coordinated attempt to sort of upgrade network infrastructure to support the deployment, as it were. And at the end of the day, always is sort of about trying to prevent blackouts. And hopefully, yeah. I mean, I don't want to get into the Nigeria talk right now, but there is a lot of actually evidence that this can work in terms of the modeling, where flexibility services can maintain the grid, and especially EVs, for example, but actually just any local load connected at distribution, if it can be automated or coordinated, can result in massive savings in both cost and carbon, which is quite exciting. Really, as a summary, and is trying to then, from a research perspective, at least from my particular understanding, AI in our particular field, it's sort of not a one fit size for all, and there are a lot of questions about it. The key advantages are that it's very fast and it's able to analyze a lot of points very quickly that perhaps may need further investigation. But for AI to support operations and control, it needs to be managed. All the risks in there, and need somehow, I think, opens the door for the physics-informed research questions, and further questions regarding sort of the generalization and the consistency of solutions relative to what the known physics is, has a lot of opportunities for subsequent research. But I think it's also quite interesting to hope to see some of these being used in real time and tested in some environments, and some competitions are already starting to do that with, for example, the run a grid challenge with reinforcement learning. And I see sort of a future where sort of flexibility is going to be very key and crucial in distributed energy systems, and present certain opportunities that would hopefully make the system a bit more smarter and agile. And then it's sort of, how do you design tariffs? How do you design products? How do you incentivize behavior change? And how do you coordinate that? And it's sort of a mismatch of many different things coming together. Yeah, thank you very much. A little over than what I expected, but yeah, thank you, Ali, for the invitation, and thank you, everyone. I'm not sure how this goes, but yeah, if there are questions, I'm happy to engage.
Thank you. Thank you so much, Dr. Al-Amin, for an insightful presentation. So we'll take questions. I think the first one is from me. When you drop, for example, the railway system, as you know, the railways, we can power them by diesel, or there's also electric traction, where the traction is from electricity. So if you drop this idea of powering vehicles such as railway vehicles into the pool of what we've discussed today, how can this your work, how does it, is there a way that that it fits in?
Yeah, thank you for your question. I just rephrase it back to you just to make sure that I understand it quite quickly. You're asking how sort of you could use I think more clean energy to power rails. Is that it?
Yes, yes, more efficient, so that we don't have
More,
larger power losses. And
yeah. So again, not an expert in the rail systems and not quite sure how they sort of get their energy. But certainly, I think with stuff like I think rail or other things that sort of have patterns, from an operational and planning perspective, it's sort of quite easy to accommodate that. But also, I think certainty, at least from that perspective, is always somehow good. So, from an operational perspective, as long as I know, as a system operator, I know I'm going to need X amount of energy here to power this. The trains have these schedules and run between X time and Y time. Um, there's a way that sort of you can sort of accommodate that into sort of the um, into the system. The challenge sometimes, what as I see it from a grid scale perspective, is if you want to say, for example, match that with the time when renewable energies are sort of high, it's not always the case that when there's a lot of demand, it's when sort of the output is going to be quite high, which then sort of opens out the questions of, can you store that energy somehow in a bit more interesting ways, or in a bit more efficient ways, and then you can rechannel that? Or can you get to that energy elsewhere? And really, in a system, and again, it requires a lot of automation, which depending on where you are, for example, in Europe, people are not quite open to sort of such ideas. But if you're able to play around with sort of that demand, obviously there are all these services where, if as a customer you are able to be flexible with your demand, you can get paid for being flexible. But really, what it does mean is that you can actually phase out all the dirty energy, using all clean energy, and you can then play around with that flexibility, sending in power from one side of the network to support sort of the other side, in such a way that you know, you wouldn't need sort of that extra dirty fuel certainty to be able to cover that. I think what was is, from an operational perspective, very very great, I guess, with sort of like coal and gas power stations, is the certainty of sort of generation that sort of you have. And if you are able to address that certainty in another way, which flexibility can, you know, then you're able to then sort of power not just rails, but quite anything, as long as you know, demand is responsive somehow, and it's following generation rather than the other way around. I'm not sure if this completely answers, but
yeah,
sort of in that
well,
direction.
a bit more on railways. Sorry.
Yeah.
So countries like France, Hong Kong, you know, they mostly use DC to power their railways, and then
Mm,
in other climes you have AC. You know, you want to increase the voltage, you want high voltage, and so that you have less power loss. So uh, with this in mind, uh, would you argue that independent power systems, in Lagos, for example, the way they are doing their blue and red line is to do independent power systems instead of sourcing power directly from like the center.
mm,
Yeah. So would you argue that these kind of systems, since they actively require power, uh, will you argue that they should have a separate, dedicated
mm.
power system?
Yeah. Again, I think it's such a, so there are different ways that you can. It's a really good question, firstly. but there are separate ways I think that you can conceptualize that, and you can think about how to approach it. From a technical perspective, I think the answers are sort of there, but the question is, what's the climate there? What's the political will there? What is the strength of the system? So in a context like, for example, Nigeria, for such a sensitive stuff, it's very easy to argue that it's safer to sort of have your own independent system, connected in there, such that, I mean, not just for reals, individual people generate the power that they consume in some way to augment the electric supply. Now, however, is that the most efficient way to do it from a whole system perspective? Now that's a separate question, and I would argue not. And so if you look at accumulated demand profiles of different countries, you would find that there are peak and off-peak hours, right? And what it means is that so firstly, you have to design your system or your power system to be able to match those peak hours. So in 24 hours, it could be that, just as an example, your average consumption is, say, 100, 100 megawatts hours that you're sort of churning out. And then at one point between, say, 4 to 7 p.m. or in the morning, your demand consumption then, triples to 300 megawatt hours. Now, your system needs to be able to, supply that 300 megawatt hours and not collapse and fail. However, actually, majority of the time, you're only supplying 100 megawatt hours. Now, what's exciting with flexibility is that, well, if people are going to sort of have these so-called energy smart appliances, and it could be just an example with EVs and stuff, because it's quite easy to conceptualize, and you have sort of little batteries in these cars, as it were. So what you can do is, if everyone has their, let's say, EVs plugged in, and you have millions of cars, in the off-peak periods where, there's not a lot of energy demand, then people can sort of charge sort of those cars or batteries or whatever. I think, let's say, batteries that are distributed in the system that are low cost in a way. So if you have all of those available, then in those periods of high peak, or in periods where you want to improve the certainty for your rails, as it were, then all you have to do is tap into sort of those battery packs or the EVs or energy smart appliances to supply that. And really, if you sort of do a whole system modeling approach to it, then you can move power from one side of the country or one side of the, across countries. In fact, I mean, there are DC transmission lines, powering continents and stuff. So honestly, I think it's definitely much more efficient, much smarter to sort of do it in this way. I think it's expensive and slightly, it's not a neat solution. Like, it's a solution that works to, like, just give them independent stuff, but actually from a whole system perspective, I think if you can have automation, flexibility is sort of the way to go, or it's an efficient way to solve the problem of intermittency.
All right, thank you. Can you see the chats? The chat section.
Yeah.
There are a few
So
questions.
okay, thanks for the information. What's becoming a researcher? My question is simply to ask, what career path would be more self-beneficial for a prospective researcher in EE fields, a company R&D researcher or researcher in academia based on your experience on both sides. Um, Thank you very much, Zayad, for this question, and thank you for enjoying it. Honestly, so it's quite an interesting way to think about it from, yeah, what career path would I advise? And I think maybe both from the way we were raised, but also the way I think about stuff. I am very careful not to tell people to sort of go towards this field or that field. But maybe there are guiding principles, as it were, because ultimately, I think if you're really quite passionate about learning stuff, about growing, about improving, then it somehow doesn't quite matter what you do. Somehow it all converges towards the end. And I think electrical engineering is probably one of the widest engineering fields out there, in that the streams of possibilities of the ideas of research are going into so many different stuff. Depending on how broad you want to be, you know, back in Nigeria, like electrical at some point was also doing stuff regarding telecommunications, was doing stuff regarding computer engineering, was doing stuff with electronics, was doing stuff with high voltage power systems, was doing stuff. So there are many different ways that you can think about. Now, obviously, from a communication perspective, for example, 5G and sort of those things are quite hot right now in terms of infrastructure. I feel like in the next decade, and it could be just bias from my personal experiences, the question of energy, the question of power is quite front and center for different countries around the world and for different reasons. For example, in worlds where sort of you have sort of these matured grids, there's this question about how do you make it more agile and flexible? Um, and then for countries where the energy access problem is sort of still in its infant stages, then there are questions of sort of how do you design sort of power systems that are fit for the 21st century for them. So, I mean, I see more of the problems from the power system perspective, but I feel like really, and not just electrical engineering, whichever field of research sort of you go towards, there are a lot of interesting problems, there are a lot of interesting questions to answer. What you require is sort of to have that curiosity and open mind, and try as best as you can to enjoy what you do or do what you enjoy, because it's not something that you casually pick up and drop off, which I do sadly most of the time. But if you have a lot of interest and stuff, it helps if you're quite interested in what you're doing. I hope this answers a little bit. And then just on the side, yeah, everyone is sort of doing AI stuff. It's for me, I think it's important to have an idea about it, but yeah, you don't necessarily have to go in that direction. I think they're like fundamental problems. If it helps solve a fundamental problem, all good. Otherwise, don't get lost in the yeah fab. Okay, thank you. I hope that somewhat answers. If not, just maybe ask me like a direct question. I'm happy to try to answer. The next question goes, with your research, how can advanced machine learning techniques be leveraged to enhance the resilience of power systems against climate-induced disruptions, while minimizing their environmental impact, especially in Nigeria? Yeah, Iman, thank you very much for your question. I think, well, there's a way, I think, to sort of compartmentalize, and I think it's really quite important to categorize the different grids that there are. And what ML can do for those different grids. When we're talking about resilience from a climate change perspective, it's we're thinking about stuff to do with events that are very few, or the events that are uncommon. So I take a step back a little to sort of say, in the design of power systems, there's this concept of reliability management, and you sort of design the system in such a way that it can anticipate or it can survive certain disturbances and certain faults. So maybe when there's a line trip or so, it should be robust enough to survive that in a way. What we're happening with climate change obviously is that you have certain extremes coming into that picture of disruptions that could happen. And when the disruptions are not previously thought about, or they've not been previously accounted for, they can somehow make it really quite difficult to engage in terms of like the response of the power systems. So I think AI in particular can help in sort of simulating some of these systems, or at least allowing the system to be a bit more agile in the way it responds. And from my perspective, sort of the especially when you're looking at it from the power systems angle, we sort of know a lot of the physics somehow in terms of sort of how power is flowing, but also the dynamics and stuff. But what's challenging is how do those sort of models translate in real time, or closer to real time, to be able to respond. And I see that, AI can help in sort of better forecasting techniques, to be able to sort of plan closer real-time operation, but also in helping, for example, system operators maybe help respond, organize the system's response to those high impact, low frequency events that are climate change induced. I think also from a environmental perspective, there's a whole separate area of research going in there on how do you minimize environmental impact, which I'm not quite sure I'm qualified enough to talk about that. But I know there's a lot of stream of research going in the direction where you're trying to then see how can you do stuff with what's it called, when you sort of do adaptations and climate change risk mitigations and all of that. Yeah, I hope this answers your question. Okay,
Thank you.
a final one.
Okay.
Yeah, okay. Thank you for your presentation. My question is, you talked about a possible solution to mitigate the effect of lack of electricity in sub-Saharan Africa, particularly taking Nigeria's case study. How could your solutions be implemented? So thank you, Ali. It's obviously a very great question in there. So again, because I think the systems or data-driven systems are somewhat system agnostic, they are able to, you can translate these quite easily, scale it up, scale it down to different systems and sort of apply there. However, I think the Nigerian context is very quite peculiar in that, in my experience, and I may not have had quite the breadth of experience, but in my experience, some of the challenges bedeviling the power systems are actually not technical at all. From what I understand, there is the Nigerian factor in there, somehow bedeviling the problem, and the solutions to our power grids are not, as far as I like, they're the technical bits, but like we know how to solve all of that. You don't need any fancy sort of new techniques to sort of solve that, right? But the question is, how do you sustainably power or provide access to power in sub-Saharan African countries and Nigeria, with a view of the future? And that's a bit more profound a question. It's a bit more existential, you could say, in a way. And from my understanding and thinking is you probably need to develop these more off-grid energy. You need to strengthen the grid that we have right now with reinforcements. And I think there's some stuff that the previous administration and this are thinking about and currently doing. But actually, you want to introduce agileness, especially when the grid is this young. You want to sort of introduce that nimble effect rather than expand the grid. Because it's a forgive the language, it's a bloody expensive investment to sort of build our transmission lines and get all those equipment in there. A much more efficient, and I'm all thinking about efficiency in here, is actually to build decentralized systems like little mini grids, little microgrids that can help with that automation, with that sort of delivery. And then it's not just, I think, about my work, then there are all these other sort of streams of research that could potentially come in together. So for example, when you have those little mini grids or microgrids, there's research going in the direction of peer-to-peer energy sharing, using stuff like blockchain and stuff. You could go into, obviously, the AI stuff on ML-based stuff can help with the efficient operation of these sites potentially, but actually even in the context of the bigger grid. And then, and I think the NERC and REA are sort of doing a lot of work in this direction, where sort of the planning of the mini grids are such that if at a point later in time the grid sort of gets to their to that locations, you can easily sort of just interconnect and actually still maybe have some form of resilience built in there, because hypothetically, if the grid sort of then collapse, hopefully it doesn't, then sort of that little mini community with their mini grid or microgrid are still able to function and sort of still able to continue having access to power, which somehow I think leads to the previous question about resilience of power systems. I think that's sort of the vision of I think an energy system for those type of countries. Get decentralized systems, mesh them all up together, connect them, put them to the grid, and see how sort of use some of these techniques to help. I hope that answers your question. If not, just let me know. Give me a shout.
Okay, if there are other questions, you could just write or requests for me to unmute you so you could speak directly. Okay. Okay. I think there's another one. Okay, no, none yet. So in the absence, okay. Okay, we have another one.
Super. Okay, thank you, Doc. How do you approach ethical considerations surrounding AI implementation in the grid system? And are these systems resilient less resistance to hacking or other cyber tampering? Yeah, this is a really great question. Again, not 100%. So I have sort of some initial ideas, but it's not 100% sort of my forte. But I know there's sort of research going into the direction of cybersecurity in parallel to sort of this AI operations. Because certainly one, I think to answer the second question is there's no system that is cyber tamper proof. And they're always sort of this cat and mouse game of evolving systems where new techniques are being brought up to try to exploit systems, and then new countermeasures are being developed to try to sort of prevent those exploits and hacks, as it were. But yeah, as long as there are going to be digital systems, there's always that possibility of hacks and cyber tampering. And there's a whole field of research then going into how do you design your systems to at least minimize cyber tampering? How do you access to that information of the system operation states? Sort of such a very wide, big area of research and thinking about stuff. But in terms of the implementation, then there are some sort of considerations to be given. And from an ethical perspective, obviously, as a bad actor, you're coming with your own nefarious needs and thinking about that. But I feel like there are always going to be or like challenges to stuff, in that it's sort of a process or a means towards an end. As far as humans are concerned, any system sort of has vulnerabilities and has always been exploited by certain people. But I think it's just thinking about how do you contextualize sort of those ethical considerations? How do you contextualize those safety concerns from a cybersecurity perspective to make sure that your systems are operating well? Again, if you look at for example, conflict in Ukraine and Russia happening, there's I think at some point they were targeting the power stations, because the power station is really quite such a critical infrastructure for any nation. But it's really quite interesting how it is such a magnificent beast, the power system infrastructure. I think when these guys came back from the moon, they organized like a thing where they were trying to understand what was like the biggest, I think, man-made system, biggest sort of Marvel contribution, I think in the 60s or 70s. And I think at that conference, they came out as sort of the power system is sort of like, that thing. And what I'm trying to say is that it's such the scale of it is really quite interesting, but also the ability of it to withstand a lot of stuff. Like you can sort of attack it in a way, but there are ways to sort of always get it back up. Yeah, so it sort of makes it sort of quite an interesting perspective. But yeah, for the other person talking about asking about areas to go into research, and this could be one side of it as well, and something that is going to keep evolving, something that's going to be very necessary, but not just for power systems. I think it's more digital systems. There was some, I think, research coming out a few months or years back regarding trying to break sort of the encryption protocols that we're going to that we are operating currently. And when you start thinking about stuff in the perspective of research going into quantum computing or quantum computers coming on board, there's always that high possibilities of encryption systems being broken, as it were. But I think, yeah, it's just something that just evolves over time, in terms of sort of like an action reaction perspective. It will keep evolving, it will keep changing. It's just something that you consider in your design system. Yeah, I hope that answers your question.
All right. Are there any other questions? You could request to speak directly if you want to. Okay. In the absence of any further questions, I would like to appreciate Dr. Al-amin Bugaje for a wonderful presentation and very insightful conversation that we've had in the Q&A session. Thank you so much. And yeah, that'll be the end of the session. Thank you.
Yeah, thank you very much, Ali, again for the invitation, and yeah, audience for listening. I hope it was helpful in any way. But really, yeah, this really quite a great initiative, and yeah, kudos, keep up the good work, and yeah, thank you all.
Thank you. All right,
Awesome.
people, thank you. And this is actually the last in our series of summer seminar sessions. And so until next year, I'll see you again. Thank you very much.